these are a unique class of materials because they're based on something we call macromer technology. And that really means that the molecular species in the Lumicryl are somewhere between monomeric and high polymer in nature, typically with an atomic mass unit of several thousand. So that really differentiates them from monomeric species and high polymers. And there's an advantage, intrinsic advantage, to being in that molecular weight area. And that is with monomers, as covalent bonds are formed, there's a lot of shrinkage that occurs. The macromer technology, because it already has a fairly high molecular weight intrinsically present, there's a lot less shrinkage upon cure of the molecule. On the other hand, they're sufficiently low molecular weight that you don't run into necessarily all the problems intrinsic to really high molecular weight polymers, such as viscosity, handling issues. So someplace in between the very low molecular weight monomer, high molecular weight polymer. The technology is acrylic, which has a number of intrinsic advantages, including an unsaturated backbone, good weathering, reasonable physical properties, and good adhesion.
Being a higher molecular weight material, it is essentially covalently bonded prior to irradiation. That has several advantages. The first advantage is that there is less free space involved in the polymer matrix. And that free space, when you irradiate, if there is free space, it gets taken up. The material actually has a dimensional change. And that's what you see with classical monomers and oligomers, where they have a dimensional shrinkage. And these shrinkages can vary anywhere from 10, 15% up to 30%, depending on the functionality. We've seen with the Lumicryl macromeric technology that these shrinkages are much less, in the tune of 1, 2%. So that really aids in a primary adhesion. In addition, along the backbone architecture, we have moieties hanging off. And these moieties can be acrylate functional groups to promote UV cure, or they can have secondary functionality. And this secondary functionality can allow for another type of cure mechanism, whether you want to do a therm mechanism, or it can help actually bond the material to a substrate. We've looked at these on a number of substrates. The most classically difficult one to adhere to are your plastics. They have a very low surface energy. So the key to getting a good primary adhesion on a very low surface, doing some sort of plasma treatment or pre-treatment of it, is to get as close as you can to a similar surface energy of the coating. And we can do that by adding things like very aliphatic groups on it to lower the surface energy of our coating. Gets more contact between the actual coating and the substrate. Also, if you're looking at one of the new technologies that we're exploring is wood coating. Here, because the nature of cellulose, you have a lot of hydroxyl groups on the surface. It doesn't necessarily make it difficult for primary adhesion, but we can put moieties on the Lumicryl that can actually allow you to chemically bond to the wood. So you don't get better adhesion than when something is covalently bonded to the substrate. First off, you don't have to use isocyanate technology, so you have a handling benefit, especially if you're talking spray application. You're spraying the materials that have isocyanates, there's going to be, you look at the Lumicryl technology, it's pure acrylic. Many of the isocyanates have some sort of aromaticity involved in their backbone, so we may get better yellowing. Also, there is a bit of a price advantage. Being an acrylic by nature, it's not quite as expensive as the urethane acrylates. And you really have to check it in the specific application area to see if it gives you a demonstrable benefit in performance properties. They can actually be used both ways. As a primary binder in the resin, these materials have shown great ability for hardness, yet maintaining flexibility, which almost seems diametrically opposed. As an additive level, it can really help if you need to get a little bit better adhesion, especially to your lower surface energy, thermoplastic olefins.
There are two types of Lumicryl. One is non-solvent. These are 100% solids, no VOC. The primary advantage of the solvent-borne materials is that upon drying, forced air drying with a very non-tacky, non-blocking surface prior to UV cure, thermoplastic state. So it's possible to take that in the dry state and do some operation to it, such as sanding, bending, rolling, stacking, a finishing operation of some sort prior to the final UV cure. Upon final UV cure of the finished material, then you have achieved full physical properties, solvent resistance, adhesion, other mechanical properties. Certainly they can be diluted to some extent in additional reactive diluent. Most of the Lumicryls, with the exception of Lumicryl 1000, are provided in various reactive diluents to additionally control application viscosity. There is a possibility that they could be heated to some extent to further reduce the viscosity, depending on the application technique. If it's spraying, roll coating, doctor blade, there are many ways to apply these. Dosage, UV energy. One issue seems to be that since we're already at a relatively high molecular weight, as cure proceeds, molecular weight builds, the materials become frozen and the reactive end groups have a little bit more difficulty finding one another to achieve full conversion. That may or may not be a problem. You might well achieve full cure properties without approaching 100% conversion. So it really should be approached on an application case-by-case basis and experimentally verified what degree of conversion you require.